All right, so let's get started with a somewhat sparse crowd here. So the topic of today is assignment 6. And yes, I know that assignment 5 is still very much in progress. But assignment 6 concerns a type of phenomenon, behavior, whatever you might call it, called a buffer overflow, and its use for attacking computer systems. It is an interesting topic to think about, and people have always found assignment 6 to be one of the kind of fun assignments in the course. So it seemed appropriate to talk about it today, where everybody is itching to go on a much-needed several-day break. All right, so we are going to start by talking about the concept of buffer overruns, and we are going to then transition into exactly what you're supposed to do for assignment 6. Assignment 6 has a couple of different parts to it. We're going to cover one of the parts today. The remaining part is going to be left for next week, when we will talk about machine language, because you'll need to know a little something about machine language in order to do the more advanced parts of assignment 6. So we'll start by looking at a program. So here is a program, simple enough. Good old C asks what is your name, reads your name into an array of char. Eventually, the input reaches a new line. So you type your name, you hit return, and we are very careful. We're good little C programmers. We put a null at the end of the string that we just copied, and we print out a little bit of a message. And sure enough, the program does what it says, or does what you think it does. Asks you for a name, you type in a name, and it thanks you and tells you the answer to life, the universe, and everything. If you don't know why the answer is 42, ask the mice. The problem comes in when I try to run the program. I run the program, type in my name, the program thanks me, and something strange happens. I mean, what? Huh? Why is my name suddenly split up? And I didn't get the correct answer to life, the universe, and everything. So what is going on here? So if you kind of look at the program, you might notice something a little bit odd, which is that we are storing the name that we read into an array that we allocated on the stack, and we happened to give that an array a length of 12. And for those of us who have names longer than k characters, and have been encountering this problem all of our lives, fixed size buffers or fixed size fields for names is, well, annoying. And in this case, it went far beyond annoying. It was actually harmful. It was destructive. So let's try to figure out what actually happened here. So if we look at the layout of the stack, the layout of that stack frame, which now you are very much in a position to do, well, one of the things that we know is going to be on the stack is some sort of, return address. Main got called. There needs to be the return address from main on the stack. We know that's there. And then the local variables are probably going to be on the stack. And that consists of this array of char called name. It consists of the character C that we've been using there. It consists of this int that contains the magic number. It consists of the local variable I. That's kind of probably it. And then below that on the stack is the previous stack frame. It is whatever infrastructure code the compiler and linker included that eventually called the function called main. So all of the information belonging to that is kind of down there on the stack. All right, great. So what exactly happened when we typed in a name that was too long for the array that we had called name? Well, the loop in the code kept on going, and we started overwriting other things on the stack. This is one of those situations where you start to realize just how nice it was when you were doing 126 and cursing Java for complaining about array out-of-bounds accesses. You start realizing that that was a good thing that it did that for you, because the fact that C doesn't do it for you means that you got damage to your program through an unchecked write beyond the end of an array. So we actually overwrote the values of other variables. So this is what is known as a buffer overrun, or kind of more popularly, a stack smash. And it is considered a security vulnerability in a C program. Basically, whenever you write a C program such that user input can cause unchecked out-of-bounds accesses to the array, which can then overwrite other parts of the program, this is not what the program was supposed to do. It's a vulnerability in the program and can lead to a lot of problems. So what happens? Well, here, the buffer overrun led to overwriting certain variables that you didn't expect to overwrite. And believe it or not, that's actually the mildest thing that can happen due to a buffer overrun. Because there are things like return addresses on the stack. Well, what is a return address? Well, it's someplace in the code, it's an address that at some point in the code, you're going to read that address and go to that address, go to code at that address. So if you're allowed to overwrite that, well, you can overwrite that with, an illegal address, and that's going to crash your program. So a user, just by typing into this program, can crash it. That's bad. But again, that's not the worst thing that can happen. The worst thing that can happen is that the user is actually clever about what they put in that return address that was on the stack. That return address can now point anywhere in the code, and at some point the code will get to it, read that address, jump to that address, and start executing code from there. And that could be code that was already in the program, which is bad enough, but it could be even worse, because the user could have been clever and arranged for code to get stashed somewhere in memory. Code that the user wants to run, then arranged for the address of that code to get stashed in that return address slot where the program is going to read it, jump to it, branch to it, return to it, whatever, and start executing from there. So now, due to a buffer overflow vulnerability, the worst thing that can happen is you start executing arbitrary code. And that's not a good thing. Imagine that you are sending a request to a web server. And the web server is carelessly written, contains a buffer overflow vulnerability. And you send the web server a search term, or a malformed URL, or input in from a web form that is, too long, or crypto keys through the secure sockets layer, or something where the web server is careless and allows a buffer overrun. Well, so now you as a user have just gained control over the web server and can use it to execute arbitrary code on that web server. Not so good. What about the other way? What about if you are a client of a web server? In other words, you are on your laptop browsing the web, and the web server is malicious. It sends you something like an HTML page, or an image, or a URL. And suppose that your web browser contains a buffer overrun vulnerability. So now, whoever's running that web server has taken over your laptop. And, can use it for whatever nefarious purpose, stealing your credit card. And, you can imagine any kind of program that communicates with someone else that accepts input. If it's careless about checking that input, if it allows a buffer overrun, then that program can be attacked. And over the years, there have been vulnerabilities in not just web browsers, but also email clients, PDF viewers, the operating system kernel itself, the networking stack, the image processing library, the cryptographic library. Basically, any piece of code that you commonly run has probably had an overrun vulnerability at some point in its history. And that has probably caused real damage to the tune of 10 to the 6, 7, 8, $9, quite literally. So, how do you get around this problem? Well, one of the ways is don't do that then. Don't include security vulnerabilities, and maybe you do that by using a language other than C. Maybe you use Java, which does check array accesses for out of bounds. Or you use a language like Python, C#, ML, Ruby, any of the popular languages these days that are designed from the ground up not to have this vulnerability. Now, what it means is that they are implicitly including additional checks into the code behind your back. So there is code that you did not write, but the compiler inserted behind your back, or the environment, the execution environment, inserted behind your back to check for buffer overruns. Does that mean that it slows the code down? You bet it does. But the consequences of a security vulnerability are so big that in an awful lot of cases, this is worth it. But let's say you do want to use C. Maybe you really need the efficiency of being able to fine-tune your code, optimize your code, get it running as quickly as possible. Well, at that point, it is up to you as a programmer to exercise discipline, to read the details of the functions that you're using. There are some functions that are inherently unsafe. If you look at the man page of the getS function, it tells you never use getS. Doesn't get much more clear than that. Because it is fundamentally impossible to use getS in a way that is safe. Just the interface of the function doesn't allow it, can't be used safely. But there are a lot of functions that can be used safely. For example, instead of string copy, there is a string n copy, which allows you to specify a maximum number of characters that gets copied. And of course, if you are accessing arrays, you as the programmer need to be very careful to go through all of those accesses and make sure that you have verified that no matter what the user does, no matter what the user types in, you can't access the array beyond the bounds that you've allocated. Now, there are additional defenses against buffer overrun vulnerabilities. Some of these are in the operating system itself. Some of them are done by the compiler. It's things like randomizing the initial stack pointer so that it's much harder for a program to know what the actual addresses are going to be. It's things like no execute permissions. Remember when we were talking about page tables, we said that you can actually mark certain page tables as executable or non-executable. So the operating system will mark your stack as non-executable by default. Stack canaries. So this is something that is added to your program by the compiler. It's basically an extra little bit of data at the end of each stack frame that is set, one of the popular ways is to just set it randomly. And now, before loading up a return address and jumping to that address, what the code will do is check to make sure that those values have not been changed. And because it was set randomly, it's hard for an attacker to know what to write there in order to preserve those canary values. So there are mild mitigations that you can apply. And in a lot of cases, those have prevented a lot of harmful attacks over the years. But several years ago, there was an attack nicknamed the Heartbleed attack. It was an attack against one of the major libraries that implements cryptography. So it's basically the library that is used by your web browser to establish an encrypted connection to a web server. And there was a buffer overrun in that library, and people figured out how to exploit it, and it caused an estimated $500 million worth of damage. That one attack, before it was fixed. So imperfect mitigations, but still better than nothing. But the punchline is you as a programmer have to be very, very conscious of what your code is doing. You have to be very conscious of potential security vulnerabilities in that code. So now, on to assignment 6. In assignment 6, we are going to give you a program that is going to tell you your grade. And we have coded it up rather carelessly. So, as in that title slide, there's something that you're going to be able to do in order to affect your grade. So, what does the grader program do? It asks you for your name, and then it proceeds to check whether your name is Andrew Appel, and if it's not, it proceeds to give you a D. Now, my name is not Andrew Appel, and so when I run the program, it gives me a D. And similarly, when you run the program, your name is not Andrew Appel either, so you will enter your name, and the program will give you a D. Who is Andrew Appel? Andrew Appel is a professor in the computer science department, world expert in programming languages, and in his spare time, he does things like, crack voting machines and testify about their vulnerabilities in front of Congress. So he's kind of an expert at buffer overrun attacks. And incidentally, he's the one who created this assignment many, many years ago. Okay, so you're not Andrew Appel, but all is not lost. Because when you look at the grader program, well, there's a function that sort of asks your name and then reads your name. If you look at the function that reads your name, there's a buffer in there. And the buffer is a fixed size buffer allocated on the stack. And oh, looky here, there is no check for whether you're writing beyond the end of a buffer. And so there is an opportunity here. You can actually exploit the buffer overrun by carefully constructing a string that you enter, and you might be able to get the code to give you something other than a D. So how's this going to work? Well, obviously, you are going to construct input that smashes the stack deliberately. So the first thing to do when you're trying to figure out how to smash a stack is to figure out what is on the stack. And one of the things that is part of assignment 6 is we're going to ask you to figure out exactly what is on the stack and exactly what it is. That is, we're going to ask you to construct a memory map of the stack section of code. So you're going to need to figure out what the different stack frames are on the stack. You're going to need to figure out what are the addresses at which they live. And you're going to need to figure out what variables and what other pieces of data go where on that stack. So we know that there's going to be some stack frame belonging to main, some stack frame belonging to getName, some stack frame belonging to readString, and eventually in readString's stack frame, there is going to be some section of that is allocated to the buffer. And so you know that the attack is going to consist of overflowing that buffer and eventually starting to write in some other functions stack frame, such as getNames stack frame. So what is in there? Well, somewhere in there is a saved return address. The return address that getName is going to use to return to main. So your job is to, well, override it. And the next question is, what do you override it with? Well, let's look through the code. Hey, look, there's a line there that assigns you something other than a D. Great. So if you can figure out the assembly language in the main function, well, somewhere in there, there's going to be a bit of code that checks whether your name is Andrew Appel. And if it is, it's going to give you a B. Well, you don't want to run the am I Andrew Appel part, but the, give me a B part, yeah, that'll do. So if you can figure out where that instruction is in the text section of code, you can smash the stack, you can insert the address of that function so that getName returns to that location instead of where it otherwise would have returned in main. So this is the so-called B attack that is part of assignment 6. It is one of the attacks that we're going to ask you to execute against the greater program. Now, going back and looking at the code, you notice that there's this weird little line of code that I didn't talk about. It says mprotect something something. Why is that in there? Well, turns out operating systems have gotten good enough that since we created this assignment, operating systems have evolved to make this particular attack impossible. Actually, not this particular attack, but the A attack. It's gotten to the point where that's impossible. So we've deliberately disabled one of the protections that the operating system gives programs, namely setting certain sections of memory to be non-executable. And that's what this mprotect does. Okay, so we've made life just a little bit easier on you. All right, so how are you going to do all of this? Well, you obviously need to construct an attack string very, very carefully. And you can't really type weird characters and nulls and things like that from your keyboard. You certainly can't type them reliably. So the way we're asking you to construct this attack is to actually create a program. Create a program that creates a data file that you're then going to run the greater program with input redirected from the output file of this program, if that's complicated enough. Okay? So by using a program to write data that is going to be read by another program, you're able to very carefully control, byte by byte, bit by bit, what the greater program reads. And so here's what it needs. First of all, you need to write your name. If your name is longer than the buffer length in this assignment, sorry, you're going to have to shorten it. All right, so you're going to need to write your name. Then the next thing you're going to need to write is a null character. That is the character with an ASCII value of 0. Why? Because that's the end of string character. And so when the code prints out your name, that's when it's going to stop printing. Because you want it to print out your name and give you a grade, and not print out the rest of the junk that you're attacking the program with. So you need to include that null character. Then you need some filler, basically enough so that you get to the end of the stack frame that is reading all of this stuff and very carelessly sticking it in a buffer. The easiest thing is, just a bunch of nulls or whatever characters you want. Easter eggs are fine. And finally, for this attack, you need a single address. That is 8 bytes, because we're on a 64-bit architecture. So an 8-byte address. In C, this is spelled unsigned long. And it needs to be the address where the code can go to in order to give you that B that you want. And that's about it. Yes, question? Oh, I don't remember. I don't know. Where is it at the beginning? Is it at the do you remember? I don't remember. Something you're going to have to figure out. More questions? Simple enough. All right, there's one more part to this assignment, which is not getting thrown in jail. Exploiting a buffer overrun or any sort of security vulnerability on a computer system in order to gain financial advantage or attack the US government or attack interstate commerce or anything like that is against US law, specifically Title 18, Section 1030 of the US Code. The very first question that you should answer is, how bad is it? So one of the questions that you have to answer in your README is to go through all of this legalese and figure out how long you can get thrown in jail for if you do this illegally. And this is our way of making you go through the pain of reading legalese so that you don't go through the pain of getting thrown in jail. So you are authorized to attack the greater program, period. You are not authorized to use this new knowledge that you have for any other purpose. All right, so summary. Buffer overruns. We talked about the principle that in C there are no protections against accesses beyond the bounds of an array. And we talked about how you're going to exploit that for assignment 6. End game, rest of the course. Next week, there are 2 precepts and 2 lectures. So the first precept is going to be going over this attack in kind of one level of detail deeper, figuring out how you get that memory map, how you answer that question of just where the heck is X30, and also talking about writing to files and writing binary data. The final 2 lectures, we're going to be talking about machine language, and that is the bit of knowledge that's going to let you get something better than a B. And we're finally going to finish up that 4-stage build process that we sort of started the course with. We're going to talk in detail about what the linker does and how it does it. The final precept is the A attack, the details of that. Turns out you're actually going to write what we call a mini assembler to create machine language for instructions that you need. And that is going to be covered in the second precept of next week. Next week ends the course. There are no lectures and no precepts after next week. Assignment 6 will be due on Dean's Date. And after that, there is a final exam in this class. Final exam is on Tuesday, December 21st, 7:30 to 10:30 p.m. in McCosh 50. In person, synchronous, pencil and paper, old school exam. Boo. Sorry, we begged and pleaded with the registrar not to do it in the absolute last final exam slot, but got turned down. There will be plenty of material to help you study for the final exam. There will be a review session, most likely the Thursday after Dean's Date at usual class time. All of these details will be posted, and meanwhile, have a happy Thanksgiving break.